In the previous video lecture, we discussed about the equivalent resistance on one edge of a cube. Now in this video lecture, we will be discussing another example in which we are asked to find out the equivalent resistance on the face diagonal of a cube. So by a face diagonal, we means that between point A and B or in between point C and F, these are basically the face diagonal of this cube. So we are asked to find out the equivalent resistance between point A and B. And the rules which we used here to find out the equivalent resistance between point A and B is the symmetry and the equipotential rules. So basically we have already discussed in the previous video lectures that what is basically a symmetry in the network and how to solve a complex circuit if there exists a symmetry in that network. So if you missed that video lecture already, then the link is in the description below. Now in order to simplify this network, first of all, we will be looking for the symmetry in this network. So if there exists a symmetry in this network, then it will be easy for us to simplify this network. So if you analyze this network briefly, then you will see that point F and C are the symmetrical points because point F and point C are at the same distance from point B, and point F and point C are at the same distance from point A. So we can say that these 2 points are symmetrical points. The potential at this point will be the same as the potential at this point. So we can say that these 2 points are equipotential points, and same is the case for these 2 points, point D and point G. These 2 points are also symmetrical points because point D and G are at the same distance from point B, and point D and G are at the same distance from point A. So these 2 points are also symmetrical points. So the potential at this point will be the same as the potential at this point. So now we can simply say that point F and C and point D and G are equipotential points. Equipotential points due to the symmetry. Now let's redraw the simplified version of this network. So let's say this point which represents the point A, and this point which represents this point E. Now this point which represents this point F and C, because these 2 points are equipotential points. So this point represents the point F and C. And now this point which represents this point G and D, because these 2 points are equipotential points. So we can say that these 2 points are point G and D. And now let's say this point represents the point B, this point B, and this point represents this point H, point H. So now in between point A and E, we have this resistor R. In between point A and E, we have a resistor R. Now in between point A and F and A and C, we have 2 resistors connected. Now this E point is connected to 2 more resistors, which is the one is from E to G and the other is from E to D. So this E point is connected to 2 more resistors. Now in between point C and D, we have this resistor R. Point C and D, we have this resistor R. And in between point F and G, we have another resistor R. Point F and G, we have this resistor R. Between point F and B, we have another resistor R. Now in between point C and B, we have this resistor R. Now in between point G and H and in between point D and H, we have 2 resistors connected. Now in between point D and H and in between point G and H, we have 2 resistors connected. Now finally in between point B and H, we have this resistor R. So now basically this is the simplified version of this complex problem. And we are asked to find out the equivalent resistance between point A and point B. And each of these resistors is having a resistance of R. So now if you look into this network, then you will see that these 2 resistors are connected in parallel. These two, and these 2, and these 2 resistors are connected in parallel. So now we can use the rules of series circuits and parallel circuits to find out the equivalent resistance between point A and point B. So let's say the equivalent resistance of these 2 resistors is 1 divided by RA is equals to 1 divided by R plus 1 divided by R. So RA from this equation will be equals to R divided by 2. So now let's replace these two resistors, these two resistors, these two resistors, these and these two resistors by its equivalent resistance. So now let's say this point which represent this point A. So in between point A and FC we have these two resistors. Let's replace these two resistors by its equivalent resistance of R divided by 2. And in between point A and E we have this resistor which will be the same as resistor R. Now in between point E and GD, this is point E, we have this resistor which is the equivalent of these two resistors, which is R divided by 2. Now in between point FC and GD we have another resistor which is the equivalent of these two resistors, which is also R divided by 2. And the equivalent of these two resistors will also be R divided by 2. And this is point B. And in between point GD and H we have another resistor R divided by 2, which is the equivalent of these two resistors, and this resistor will be the same as it is, and this is point H. So now if you look at again into this network, then you will see that these two resistors are connected in series and these two resistors are also connected in series. So now let's replace these two resistors and these two resistors by its equivalent resistance. So let's say RB is the equivalent resistance of these two resistors, which is equals to R divided by 2 plus R, which is equals to 3 divided by 2 into R. So the equivalent is 3 divided by 2R, and its equivalent is also 3 divided by 2 into R. So now if you look at carefully again into this network, then you will see that there exists a vertical symmetry in this network, because if we draw a vertical line which can join these 2 points, point FC and point GD, then you will see that this side is the mirror image of this side. So we can say that there exists a vertical symmetry in this network. So we have discussed already about the vertical symmetry in the previous videos. So in the vertical symmetry we know that the current will be the same at the symmetrical paths. So basically this resistor is the mirror image of this resistor. So we can say that if there is a current I1 through this resistor, then the same current will be through this resistor I1. And if there is current I2 through this resistor, then the same current will be through this resistor, because this resistor is the mirror image of this resistor. So from this you can easily say that this current is flowing through this resistor only, and this current is not following this path. And the same is the case for this current. This current is flowing through this resistor and this resistor only, and not following this path. So we can say that the current through this path will be equals to 0. So we can say that there will be no potential difference across the terminals of this resistor. So we can remove this resistor from our analysis. So the simplified version of this network will be, let's say this is point A. So this one is this resistor R divided by 2, and this resistor R divided by 2, and this is the point B. And this resistor also 3 divided by 2 into R. And finally this resistor is connected to point B, which is 3 divided by 2 into R. So now if you look at into this network, then you will see that these two resistors and these two resistors are connected in series. So the equivalent of these two resistors is, let's say, RC is equals to 3 divided by 2R plus 3 divided by 2 into R. So RC will be equals to 3R. Now the equivalent of these two resistors will be equals to, let's say, RD, it will be equals to R divided by 2 plus R divided by 2. So the equivalent of these two resistors, let's say RD, will be equals to R. So now let's replace these two resistors and these two resistors by its equivalent resistance. So let's say this is the point A. So in between point A and B we have this resistor which is equals to R, which is the equivalent of these two resistors. And in between point A and B we have another resistor which is 3R. which is the equivalent of these two resistors. So now if you look into this network, then you will see that these two resistors are connected in parallel. So now the equivalent of these two resistors will be, let's say, 1 divided by RAB will be equals to 1 divided by R plus 1 divided by 3R. So RAB from this equation will be equals to 3 divided by 4 into R. So this is basically the equivalent resistance on the phase diagonal of this cube. Simply we can say that this is the equivalent resistance between point A and B of this cube. So it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.